All right, guys, let's go over this foldable here. The front looks like this, but these are all in order, like top, middle, and then this is on bottom here. But I just kind of rearranged it so it fit all on the screen. Now, we're not going to write anything on this sheet. I'm just going to kind of go over and explain it. But this foldable, what I did is I folded this like a book, where this will be the front cover, and then the other two would be like on the inside of the book, and then I pasted it just in one page in my interactive student notebook. So that's how I did that. All right, so the first theorem we're going to go over is the linear pair perpendicular theorem. Okay, so this one here. So it says, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So the key words here, guys, is linear pair and congruent angles. Okay, so if two angles are linear pair and they're congruent, then that means that G and H have to be perpendicular. Okay, so here we go. If angle 1 and angle 2 are a linear pair, which they are a linear pair, and if they're congruent, which according to these same arc, symbols, they are congruent. Because that's the case, then that means that line G and line H are perpendicular. Okay, so let's think about that for a little bit. So if 1 and 2 are both a linear pair and congruent, that means the measure of both angle 1, angle 2 has to be what? Okay, if angle 1 and angle 2 both have a measure of 90 degrees, then that means that G and H are perpendicular. So this one shouldn't be a surprise to you. All right, let's look at the second one. Let's look at the perpendicular transversal theorem. Okay, it says in a plane, if a transversal is perpendicular to one of two parallel lines, okay, so we have to know the lines are parallel, then it's perpendicular to the other. Okay, so in other words, if we look at this diagram, we know that H and K are parallel. Okay, that's what those two arrows right there means. Okay, and we also know that J is perpendicular to H. Well, if J is perpendicular to H and lines H and K are parallel, then that means that J has to be perpendicular to K as well. Okay, now this should make sense to you, because if you look at this, if this is 90 degrees right here, if this is perpendicular 90 degrees and H and K are parallel, then that means this angle right here is 90 degrees as well, because it's corresponding angles, and we know that when lines are parallel, corresponding angles are congruent. And if this is also 90 degrees, then that means J is also parallel to K. So you should be able to get that without this theorem, but there is a theorem that kind of makes our life a little easier. It's kind of a shortcut. All right, let's look at this last theorem. And like I've already said, this theorem here is kind of at the bottom. It goes 1, 2, this is the third one at the bottom, but just to fit it on this page, I went ahead and put it over here. So this is the lines perpendicular to a transversal theorem. Okay, so it says in a plane, if two lines are perpendicular to the same line, okay, they're perpendicular to the same line, then they are parallel to each other. Okay, so if we look at this diagram, notice that M is parallel to P and N is parallel to P. Okay, so because both M and N are perpendicular to P, that means that M has to be parallel to N. Okay, now this one should also make sense, because if we look at this, this angle here and this angle here are corresponding angles, and if corresponding angles are congruent, the converse says that the lines must be parallel. So once again, this is a theorem that we could have gotten there without using the theorem, but this just makes it a little bit shorter and easier. All right, so this is the inside of that foldable. So there's 3 here. Let me scroll down to show you. I do have a third one down here. There's 3 examples here. All right, so the directions say determine which lines if any, so some of these may not have any, must be parallel, and explain your reason. Okay, so I'm going to pause this and I want you to try on your own to do examples 1, 2, and 3, and then we'll go over the answers and the reasoning for each one. But I want you to try this on your own, and I'll give you a hint. It all goes back to those 3 theorems we just talked about. All right, let's look at these. So I've went in and I filled in the answers, but I do want to talk about them. So on example 1, we can't say for sure that any lines are parallel. Okay, they look to be parallel. L and M look like they're parallel. N and P look like they're parallel. But the places we have these 90-degree angles, notice they're not along the same line. Okay, so this is along L and N, and this is along M and P. So they don't really cross, so there's no theorems that we can use to tell for sure that any of those lines are parallel. Okay, let's look at example 2 now. Now notice here's a right angle and here's a right angle. Okay, now if this is a right angle, guys, then this has to be a right angle, and all the way around it has to be right angles. Okay, so if at one intersection point, one of the 4 angles is right angle, all of them have to be, because they're all linear pairs. So therefore, they're all supplementary. So if we look, both of these perpendicular angles, or both of these right angles, is along line E, right? So I can say that that means E has to be perpendicular to G, and that means E has to be perpendicular to H. Okay, well, the lines perpendicular to a transversal theorem tells us that if one line is perpendicular to 2 different lines, then the 2 different lines has to be parallel. So we can say, we can confirm that lines G and line H are parallel because E is perpendicular to both, and the theorem we would use is the lines perpendicular to a transversal theorem. All right, let's look at example 3 now. Example 3 is very similar to example 2. So we have both of these right angles, and both of them are along line A. Okay, so I can confirm just by looking at this diagram and looking where the right angles are that A is perpendicular to B and A is perpendicular to C. And once again, the lines perpendicular to a transversal theorem tells us that if the same line, so in this case the same line would be A, if the same line is perpendicular to 2 different lines, so line A is perpendicular to both B and C, then the 2 different lines, which would be B and C, has to be parallel. So I can conclude that B is parallel to C because A is perpendicular to both B and C. All right, let's look at proof number 1. All right, so we're given that angle 1 and angle 2. We're given that F is parallel to H and F is perpendicular to H, and F is parallel to G. All right, so on number 4, it says E is parallel to H. Okay, well, we don't have a right angle here. So how do I know that's true? Okay, well, let's go back here. We know that angle 1 is congruent to angle 2. Okay, and we know that angle 1 and angle 2 are a linear pair. And so remember, the line pair perpendicular theorem tells us that if we have a pair of congruent angles that are also a linear pair, then they have to be perpendicular. Okay, so that's why they're perpendicular. All right, so now I want to look, and if I know that line H is perpendicular to both line E and line F, then I can say that line E and line F are parallel. Remember, that theorem we just learned is lines perpendicular to a transversal theorem. Okay, that theorem says that if we have one line that is perpendicular to 2 different lines, and those 2 different lines are parallel, which we have. So I can say E is parallel to F. Well, guys, if I know E is parallel to F, and I know F is parallel to G, then that means E has to be parallel to G by the transitive property of parallel lines. All right, let's look at the second and the last proof here. Okay, so it says angle 1 and angle 2 are congruent. And then it says that B, so if they're congruent, I'm just going to put that in that. That means they have to be 90-degree angles. Then I know B is perpendicular to D, so that's already shown. And I know C and D are parallel, so both of those arrows show that they're parallel. Okay, so I have all that. All right, the linear pair perpendicular theorem, guys, tells us that if two angles are both a linear pair and congruent, so in this case we're talking about angles 1 and 2, then these two lines have to be perpendicular. Okay, so this would be A is perpendicular to line C. Okay, these have to be 90-degree angles. If these are 90-degree angles, this is perpendicular here. All right, now if I know that C and D are parallel and A is perpendicular to C, doesn't that mean that A has to be perpendicular to D as well? Because the perpendicular transversal theorem. And then if I know there's a right angle here, I just said these are perpendicular, so that's a right angle. Well, now I have line D, which is parallel to both A and B. So lines perpendicular to a transversal theorem. I would use that again, because if the same line is perpendicular to two different lines, those two different lines has to be parallel. So that would be our second proof, and that completes our foldable.